recurring decimals. So recurring decimals have numbers that go on forever, and sometimes even groups of numbers that go on forever. So an example of a recurring decimal is a third, because if we change it to a decimal, we get 0.333333, which goes forever. And another way to write this is 0.3 with a dot above it to show that it does go forever. That's the digit that goes forever. So some more examples are 0.111111, which we could write as 0.1 recurring, 1.424242 forever, which is 0.4 recurring, 2 recurring, because both the 4 and 2 repeat forever, 0.708, 708, 708 forever, which we actually write as 0.7 recurring, 0.8 recurring. So you only need the dot above the group of digits at the start and end that repeat forever, and 0.2189999 forever. So this would be 0.2189 with just a recurring above the 9, because that's the only one that repeats forever. So if we were given a recurring decimal, how could we change it into a fraction? So let's look at 0.2 recurring. Well, that's just 0.22222 forever and ever. So to do this, we want to let x equal 0.22222 forever and ever. And we want to multiply by either 10, 100, 1,000, a million, something with a 1 and zeros, to just get another equation where after the decimal point we get the same thing. So in this case, multiplying everything by 10 is going to allow that. So if we multiply our x by 10, we get 10x. And if we multiply 0.22222 forever and ever by 10, we get 2.22222 forever. And now what we want to do is subtract them from each other. So we get 10x minus x gives us 9x. And here, all of these recurring decimals will cancel out with each other when we subtract them, and we're just left with 2 minus 0, which is 2. And now we can divide both sides by 9, and we get x equals 2 over 9. And remember, x equaled our original recurring decimal, so that means 0.2 forever, or reoccurring, is the same as 2 over 9. Let's have a look at another one. 3.48 recurring, which is the same as 3.4888888 forever and ever. So going to start off the same. We're going to let x equal 3.48888. But we always want to get the recurring numbers only after the decimal. Here we've got a 4 that's not reoccurring, so we need to at least times it by 10 to get it in front of the decimal. So let's go ahead and do that. So we'll times everything by 10, so we get 10x equals 34.88888. But we need two equations where everything after the decimal is the same. So let's go ahead and multiply the equation we just got by 10 as well. So 10x times 10 is 100x. And 34.88 times 100 gives us 348.888 forever and ever. And now we can go ahead and minus these two equations from each other, because everything after the decimal is the same. And they're gonna all cancel out with each other when we subtract them. So 100x minus 10x gives us 90x, and And 348 minus 34 is going to give us 314. Now we can divide both sides by 90. So we get 314 over 90. It's going to simplify to 157 over 45. Let's have a look at one more example. 1.305 with recurring above the 3 and the 5. So that's 1.305, 305, 305 forever and ever. And we're going to let x equal that. So 1.305, 305, 305 forever and ever. And we need another equation that has the same thing recurring after the decimal. So if we multiply both sides by 10, we'd get 053, 053 recurring, which is not the same. We need to start with the 3. So we're going to have to move the decimal 1, 2, 3 places. So we're starting with the 3 again. So we're going to have to multiply by 1,000. So let's multiply x by 1,000 to give us 1,000x. And multiplying this by 1,000 is going to give us 1,305.305, 305, 305 forever and ever. That's exactly what we want, because when we subtract them, all of these will cancel out with each other. And we get 1,000x minus x is 999x. And 1,305 minus 1 is 1,304. Divide both sides by 99 will give us 1,304 over 999 is our final answer.